Welcome again to the Jerusalem Science Contest. Today we'll be doing Chapter 16, The Ocean Depths, and this will be, I believe, the 11th lecture. There should be two more following this one. So this is a very interesting chapter. It turns out, had I read this chapter in advance, I probably would not have given you as extra credit questions all the ones that I gave you on bioluminescent organisms, because there's actually quite a bit of information in this chapter on bioluminescent organisms, and some of that material was stuff that I had presented to you, not realizing that it was actually in the book. So I gave that to you several weeks ago, and in fact I won't be testing you on that material again unless it's something that I didn't already ask. I mean, if there's anything in the book that I haven't already asked, but most of that material probably was already covered in previous lectures. So what I'd like to talk to you about today, there are still a lot of other interesting things in the book that we could expound upon, and one of them actually has to do with the fact that you've got organisms that are living, in some cases, under tremendous pressures. The pressures may be as much as 1,000 atmospheres, and those great pressures have a certain effect on enzymes and enzyme activity. So we could have discussed that, and perhaps I'll do that in a later lecture if time permits. But what I'd really like to talk to you about today is something that I found very intriguing, and that has to do, and it is covered in your book to a small extent, and I'm actually going to refer you to. It's actually right at the end of the chapter, and it's on page 380. And there's an organism that's shown there, which is the hydrothermal vent tube worm, Riftia Pachyptilla. Now, this particular organism is very, very interesting because we've seen tube worms. I've even shown you tube worms in my 60-gallon aquarium. And if you remember, those tube worms have a sort of filamentous plume that they extend out of the tube, and they use this as a means of feeding. So they can actually attract small amounts of matter onto the plume. They can hold it in the plume, and then it can be drawn inside into the buccal cavity. It turns out that these other tube worms, the ones that are living at great depths in the bathypelagic zone, these particular worms, such as Riftia, they don't function in quite the same way. They have the plume, and you can, let me see if I can show this picture so you can see what I'm referring to here. So here's the, I'm trying to hold this up here, so you can see the plume right over here. Whoops, see the plume right here. And you also notice that right underneath the plume there's kind of a collar, and it's indicated where the collar is, that this is the heart. Now underneath the heart is another structure which is referred to in your book as a trophosome, or feeding body. And I really want to talk a little bit about the trophosome because it's such an unusual structure and such an unusual organ. Now in the book we learn, when we look at the book, that there are bacteria living within this trophosome, and the picture that's in the book that shows the bacteria as kind of free living structures in the trophosome is not entirely accurate. I'll talk about that in a moment. But I do want to talk a little bit about the structure of the trophosome and what's actually going on inside the bacteria. So you'll notice that there are two blood vessels to either side of the trophosome, and one of them is referred to as dorsal, and the other one is ventral. So the dorsal one would be on the backside of the animal, and the ventral one would be on the stomach, if you wanted to call it that, or the front side of the animal. And in between that, we actually have the trophosome. If you looked at the tissue of the trophosome, you would find that it's green in color, which is unusual, because if you actually look at the picture of these worms, you'll see that they're kind of bright red in color. You can see them up in the top here. Let's see if I can get this in focus here. You can see there's a whole sea of these worms. This is one of these vent communities that you see in the top picture. There is a fish that's visible there. The fish is a zooarched fish, or it's also known as an eel pout. And there's also crabs that are there, and a lot of mollusks. a lot of clams and other kinds of organisms that also utilize bacteria but not in exactly the same way that these tube worms do. These tube worms are really kind of unique. For one thing, they're gigantic. They're about a meter when they're fully grown. They're about a meter in length. You recall that the tube worms that I have in my aquarium, on average, are probably maybe an inch or so long, and these things are 3 feet 39 inches, 40 inches in length. So you're talking about something that's really quite large, and the tube, has to be built. This very, very large tube, and there really are hundreds, if not thousands, of these organisms that are gathered around the vent. So what's happening in the vent? The vent is a fumarole, which is actually something where magma has come up to the surface, and you've got water under very, very great pressure that is coming in contact with this very hot magma. The water can actually be heated up to about temperatures as high as 400 degrees Celsius. Now, normally water, at least at atmospheric pressure, boils at 100 degrees, and you can't get it to go any higher than that. I mean, if once the temperature hits 100 degrees, the water doesn't get any hotter than that because the water starts to boil off. But under great pressure, for instance, not even under that great a pressure, for instance, the kind of pressure that's used in an autoclave, you can easily get the water temperature up to 120 or 130 degrees Celsius without having it boil. But if you want to take it up to 400 degrees Celsius, it's really going to have to be under quite a bit of pressure. So here you've got this extraordinarily hot water that's coming out at 400 degrees Celsius. And the water is laden with a lot of sulfide minerals. Now, sulfides themselves, and there's also a lot of hydrogen sulfide, the gas hydrogen sulfide, that's being produced as well. So hydrogen sulfide is extraordinarily toxic. It's toxic to mammals, it's toxic to fish, I'm sure it's toxic to most invertebrates as well. And what hydrogen sulfide does, much like hydrogen cyanide, it's known to be an inhibitor of the enzyme cytochrome C oxidase. Cytochrome C oxidase is an enzyme that's intimately involved with cellular respiration. So once you inhibit that particular enzyme, you cut off cellular respiration, and basically the organism is going to die because it's not being able to utilize oxygen in any way. Now, the difference between hydrogen sulfide and hydrogen cyanide, both of them are extraordinarily toxic. Hydrogen cyanide is something that had been used for many years. I don't believe it's used anymore in the United States. It's considered now to be, I guess, inhumane to execute criminals who are convicted of capital crimes using that particular method. But people used to be put into something called a gas chamber, and the condemned individual would be strapped to a seat, and there would be a lever that was lowered a bag containing something like sodium or potassium cyanide into a bucket of sulfuric acid, and that produced the hydrogen cyanide. And literally within minutes, the individual was dead from inhaling the gas vapors. Now, hydrogen sulfide would take somewhat longer, but the same small amount of hydrogen cyanide that would kill somebody, that same amount of hydrogen sulfide would also wind up being lethal. And I can remember an incident that occurred a number of years ago when I was out in industry, where there were actually there were workers who were not following the proper safety precautions and went into a tank. One individual went into a tank to clean it out, and the tank had been filled with hydrogen sulfide vapors, and he wasn't wearing the proper respiratory equipment, and he was rather quickly overcome by the vapors. Now, what happens with hydrogen sulfide, which smells like rotten eggs, you'd think you'd be able to detect it in at very small concentrations. And in fact, you can, but only for a short period of time, because after exposure to the gas for even a few minutes, what happens is it actually paralyzes the respiratory, I'm sorry, not the respiratory, but the olfactory nerves. So you're no longer able to perceive the odor of the hydrogen sulfide anymore. So you think you're in a safe environment because you don't smell the hydrogen sulfide. and that's probably what happened to this individual. And his co-worker, who was at the top of the tank, must have called down to him and didn't get any response. And then he looked down and he saw that his co-worker was unconscious at the bottom of the tank. So he went into the tank to retrieve this individual, again not wearing respiratory equipment, and he was overcome. And I believe that there were 4 people that actually died before somebody had enough sense to put on the proper respiratory equipment and was actually able to go into the tank and retrieve these individuals, but unfortunately none of them could be revived. So this is it just indicates how poisonous this particular gas is, and it turns out, as I said, that it does inhibit this enzyme, but unlike hydrogen cyanide, which you can actually treat hydrogen cyanide poisoning by administering certain drugs that will actually oxidize some of the hemoglobin, which actually contains ferrous iron. That's iron in the +2 oxidation state, and it will oxidize it to iron in the +3 oxidation state. So this oxidized hemoglobin is called methemoglobin, and the methemoglobin actually is capable of binding things like cyanide and also hydrogen sulfide. And the idea would be that if you could bind, certainly when you bind cyanide, it gives the body some additional time to slowly metabolize the cyanide. And the cyanide is metabolized. I'll talk about it in a little bit later, because there's actually an enzyme that I want to refer to that's involved in cyanide metabolism. That's actually important because it's actually produced by some of these worms, or at least bacteria that are in some of these worms. So the thing is, though, with hydrogen sulfide, the same kinds of drugs or treatment procedures that would actually induce the formation of methemoglobin, even though you produce the methemoglobin, those do not seem to reverse the hydrogen sulfide toxicity. So something else is